Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over an intro to Le Chatelier's principle. So let's get into this. First of all, when we're talking about Le Chatelier's principle, we need to talk about reversible reactions and equilibrium and things like that. So let's first start off with what a reversible reaction is. So a reversible reaction is basically a reaction that can go in reverse. So some reactions can either go all the way, right? So, for example, combustion reaction, you're not going to reverse that one. You burn a piece of paper, it's not going to go back to the piece of paper. You're just going to be left with ashes and carbon dioxide and other stuff that's formed during the reaction, and you can't go backwards and recreate the piece of paper from its elements. So that would be an irreversible reaction. But some reactions, they do go backwards, right? So those are the ones that we're going to be focused on with Le Chatelier's principle. So some reactions can go forwards and backwards. So here's an example. So this example here, we have nitrogen reacting with hydrogen with 3 moles to 1 mole here. And that's going to go and produce 2 moles of your ammonia. And that's going to release 92.05 kilojoules of energy. So therefore, this is a exothermic reaction, and so we write it as a product. This is going to be important when we're looking at Le Chatelier's principle with respect to exothermic and endothermic reactions and temperature changes. So when we write this delta H of the reaction, we have a negative sign because it's losing energy. Exothermic means that energy is being released out to the environment, to the surroundings, and so we're always looking at the perspective of the reaction. And so in this case, if the reaction is releasing energy to the surroundings, then that means the reaction is losing energy. So there's a negative sign, and we write it as a product. We write it as a product. Or we could have the reverse reaction. So here we have the ammonia on the reactant side. So here we just reverse this. So now we have 2 moles of ammonia gas plus the 92.05 kilojoules. So now we have the energy being absorbed or added to the system in order for this reaction to go. And that's going to produce your nitrogen gas and your hydrogen gas. And you'll notice that the delta H of the reaction is the same magnitude, same number, except now it's a positive value. Why? Because the system is gaining energy, and so it's that gaining is symbolized or represented by this positive sign. So you're gaining energy, so that's going to be positive. And so we can write both of these together using a double arrow. So we use a double arrow to represent the equilibrium. So it can go either way. Normally we write it in this way here. So we write it as the nitrogen plus the hydrogen gives you the ammonia plus the energy. And then if we want to look at the reverse reaction, we just have to change the sign of your delta H of the reaction. Um, so that's equilibrium. Oh, I'm sorry. That's your reversible reaction. This is how we symbolize or write your reversible reactions with this double arrow. If it's a single arrow, then that usually means it's not reversible, or you're just looking at one particular direction of your reaction. But typically, we write for your reversible reactions a double arrow, and for your irreversible reactions, we're writing only a single arrow. Okay, so that is it for the reversible reactions. Let's get into equilibrium. Okay, let's talk about equilibrium now. So, what is equilibrium? In a chemical reaction, the equilibrium is going to be the point at which the forward reaction is happening at the same rate as the reverse reaction. So, they're going to be going on at the same time. This is also referred to as dynamic equilibrium because the reactions are still going on, but you're not going to notice anything happening. So it's dynamic because products are being formed at the same time that reactants are being reformed from the products. So it's called dynamic equilibrium. And so what we need to understand is it's the rates of the reverse reaction and the forward reaction that are equal at equilibrium, but the concentrations are not going to be equal. So the question two, are the concentrations of reactants and products the same? No, they're not going to be the same necessarily. They could be the same. If they are the same concentrations, if products and reactants have the same concentrations, then that's just going to be a coincidence. It's not part of what we mean by equilibrium. So what we mean by equilibrium again is that the rates of the forward reaction and the rates of the reverse reaction are the same, but the concentrations are not necessarily the same. And most of the time, they're not going to be the same. So here I have a graph. The reaction that we're looking at is the decomposition of NO2 into NO and O2. And so I have a double arrow here that represents the reversibility of the reaction. So you can either have two arrows, one going forward, one going backwards, or you can have a double-headed arrow. It doesn't matter. So yeah, either way is fine. So here we have one reactant, the NO2, and that's going to be breaking down into two products, NO and oxygen. And so if you look at the graph here, you can see that at the very beginning of the reaction, when we have our reactants, we have zero products. So no products to start with, and everything we have are reactants. So when the NO2 starts to break down and the reaction continues, then what's going to happen to the concentration? So here we have concentration on the y-axis, time on the x-axis. And so you'll see that as time goes on, the concentration of NO2 decreases, and both the NO concentration and the O2 concentration are going to increase during that same time period. And so you'll notice that as time goes on, the NO and O2 concentrations go up, while at the same time the NO2 concentration is going down, and you'll reach this plateau. And so the plateau here means that you are reaching an equilibrium. So here the plateau is for the nitrogen, the NO here. And so that starts to plateau. And then these two start to plateau. And you reach a point at which they are all constant. So let me draw a line here. So that's about the line where this is where all of the concentrations stop changing, right? So at this point here, you've reached equilibrium. So the concentrations are no longer changing at equilibrium because now the rate at which your products are being made is the same rate at which the reactant is being remade from the products. So even though there really is change going on during this time, you don't see it, you don't perceive it because the concentrations stay the same during that time. And the other thing I want to point out is here, in this case, you can see that the concentrations of your products and reactants are not the same, right? So at equilibrium, they don't necessarily are going to be the same, but there's no change in the concentration at this time. So the concentrations stay what they are after the reaction has reached equilibrium. So let me recap what I just said. So here, the rates, notice at the plateaus that what this means is that the products are being made at the same rate. So we're talking about rates of reactions, not concentrations. So the same rates are going to be the same. So the products are being made at the same rate that the products are being broken back down into reactants. So the forward reaction, the rate of that reaction is the same as the rate of the reverse reaction. The other thing is that the rate of the forward and backwards reactions are the same, but we're not perceiving any change in the concentrations because they're the same. That's why we don't perceive the change in the reactions. And so again, we can see that the concentrations are not the same. So the concentrations of your products and the concentration of your reactants are not the same at equilibrium, and very seldom are they going to be. What is the same is the rate of the forward and backwards reactions. Okay, so let's talk now about finding your equilibrium point. What is the point at which the equilibrium of a reaction is achieved? Right? Let's talk about that now. Okay, so let's talk a little bit about finding this equilibrium point. Well, what is the equilibrium point? Well, the equilibrium point is found by using a ratio of the concentration of products to the concentration of reactants. Basically, it's a ratio of the products over the reactants. And so here I have an example. So I have a generic equation right here. So my reactants are A and B, my products are C and D, and the little letters represent the coefficients. And so here, the KEQ, that represents the equilibrium constant, right? So we call that the equilibrium constant K, or KEQ. And you can see that this equilibrium constant is related to the concentration of the products over the concentration of the reactants. And you'll notice that the concentrations are raised to whatever their coefficients are, right? So here I have the coefficient A, little a, and so that's raised to little a here. So it's the concentration of A raised to the little a power. So you're taking the coefficients and you're writing them as superscripts or powers. And so, but the basic thing I want you to understand is that this equilibrium point is represented by whatever the equilibrium constant for this reaction is, and that is determined by the concentrations of your products raised to their coefficients over the concentrations of reactants to raised to their coefficients. So basically it's products over reactants, products to reactants. And that's the main thing I want you to understand and keep in mind when you're thinking about Le Chatelier's principle, because it's all about changing and fluctuating, changing these concentrations to reach that equilibrium. And so a couple of things that I want to kind of point out is that you can have different ratios that all result in the rate the rate of the forward reaction being equal to or the same as the rate of the backwards reaction. So you don't have to have the exact same ratios here or the concentrations for A, B, C, and D. There's a plethora of different concentrations that you could have that would give you the same ratio and therefore the same KEQ, the equilibrium constant, right? So if you change any one of these, then you'll change the ratio, but then the reaction system will go back to whatever that ratio is. So if I decrease this, then to get that same ratio, these are going to have to change, and then you'll get the same ratio, but you're going to get different concentrations. So that's what I mean by here is that there isn't just one equilibrium point in the sense that you can only have one set of concentrations and that's it. No, you can have a different set of concentrations that will get you the same ratio, right? So that's what I'm saying here is if you are pushed away from the original concentrations, right? So if I'm pushed away from this in some way, and we'll talk a little bit about this in a moment, like for example, if I remove some of my product or if I remove some of my reactant, right? If I'm decreasing this, right? If I take some A away, right? How does the system, get back to that ratio of concentrations, right? So we'll talk about that. So if you're pushed away from the original equilibrium point or the concentrations that are going to give you that ratio, then basically you're just going to find a new set or new ratio of concentrations or a new concentrations that are going to give you that ratio that you had before, and then that'll be at equilibrium again. So it's basically having this KQ, this ratio here, stay the same, right? So how do we keep this ratio when you change things um, in the reaction? So that brings me to to talk about Le Chatelier's principle. So let's actually say talk about what Le Chatelier's principle is. Okay, let's talk about Le Chatelier's principle. So what is Le Chatelier's principle? It is that if you stress a system or a stress is applied to a reaction, because the reaction is the system in chemistry, if a stress is applied to a reaction at equilibrium, so we have a reaction that's at equilibrium, and if we disturb that equilibrium in some way, the reaction changes to relieve that stress, right? So if we do something to the reaction that disrupts its equilibrium, it will then relieve that stress in order to try to get back to that equilibrium. It will find a new equilibrium point where the forward and backwards reactions are now equal again. And so it will try to undo what I did to the system. So, for example, if I add something to the system, right, the reaction will then use some of that up, right? So, for example, if I add some reactant to the reaction mix, now I've kind of disrupted the concentrations, right? And so now the reaction is going to try to get back to equilibrium by manipulating and changing those concentrations, as I showed in the equilibrium constant expression with the products concentration of products over the concentration of the reactants. So what if I take something away, right? So if I remove some of the reactant, then it's just going to make more reactant and try to replace what I had taken away. So it's trying to undo that stress, right? So how do you stress a reaction? You can change the concentration, right? So that's like taking some of the substance away. So if I take some product away or I add some reactant, right, I've changed the concentration. I now have more reactant in the system than I did before. And so the reaction is going to try to remove what I added, right, to get back to equilibrium. Or I can take some of that substance away. So I can remove product, right? So if product is being made and it's at equilibrium, I can remove some of that product. So now it's not at equilibrium anymore because I've reduced the concentration of product that I had. And so now it's going to try to regain that equilibrium by making more product. Another way is temperature change. In earlier in this video, I showed you where you can have an exothermic or an endothermic reaction, and so that will determine where um, the energy is on your equation. So remember, if it was exothermic, I had the energy as an output on the products side. And if it was an endothermic reaction where you have to put energy in, that was on the reactant side. And so, depending on what side your energy is, that's going to determine which way the reaction is going to go in order to undo a temperature change, right? So I can raise the temperature or I can lower the temperature. And depending on which side of the reaction your energy is, that's going to determine how your system or reaction is going to react or adjust itself according to the temperature change. And also, if you're working with gases, pressure and volume changes can also stress the system or stress the system. So this is very akin to concentration changes, right? So if I decrease the volume of my gas, I'm kind of pushing those particles closer together. And so you can see that the concentration of the particles per volume or per amount of volume is going to increase, right? If I increase the volume, then am I increasing the space between particles, and the concentration is effectively decreased, right? So that's how you can change the concentration due to volume. Also, with pressure, volume and pressure are related, right? So if I decrease the volume, I'm increasing the pressure because now the particles are closer together. They're hitting up against the inside the balloon more, and so that will increase the concentration. Or I could just put more particles into my container, and that's going to increase the concentration or the number of particles per volume that I have in my container. So changing the volume and changing the pressure is akin to or very similar to changing the concentration of the gas in your container. So it's going to have the same effects as changing your concentration. Now, there are a few things we need to keep in mind with regard to Le Chatelier's principle and what's going to stress the system and what's not going to stress the system. So let's talk about that. Okay, ladies and gentlemen. So let's talk about some of these facts that we need to keep in mind regarding Le Chatelier's principle. So first, we need to keep in mind that only changes to aqueous and gas phases are going to affect your equilibrium. So that means that things that are dissolved in water, things that are gases, anything in those phases are going to affect your equilibrium. But things like solids and liquids are not going to affect equilibrium. So if you change the concentration of your aqueous solutions, or if you change the pressure and volume of your gases, then that's going to affect your equilibrium. And then Le Chatelier's principle says that the reaction or the system is going to react in such a way that it's going to undo what you did, right? But solids and liquids, they don't really have concentrations. Or another way to put it is that the concentrations of solids and liquids don't change, they're constant. So think of a solid, right? A solid has a certain density to it. That's kind of like concentration. It's a certain amount of atoms packed into a certain volume, and that doesn't really change depending on the amount of solid you add or take away. So I can change the amount of solid in my reaction vessel. That's part of the reaction, but that's not really going to affect the reaction equilibrium because I'm not really changing the concentration, because the density of the solid is not dependent on how much I put in or take out. It's the same regardless. So that's another way you can think about it. Same thing with liquids like water, right? Water has pretty much the same density at the same temperature throughout. So removing and adding water shouldn't affect my reaction, but only insofar as I'm changing the water. But if I add and subtract out water, and that's changing the concentration of my other substances, then of course that's going to affect the equilibrium, but not the water itself. The amount of water itself is not really the factor that we're looking at. So liquids, anything that's a liquid, anything that's a solid is not going to affect the equilibrium, and therefore Le Chatelier's principle is not going to apply to those. Okay, so that's point number one. And we'll talk more about the math regarding KAQ. So this has to do with the fact that your equilibrium constant expression, that the concentrations of your products over the concentrations of your reactants, that expression will not include liquids and solids, and therefore you don't have to worry about the ratio of the concentrations of those things. And we'll talk about the math more in another video. Okay, secondly, adding a noble gas, which is an inert gas, meaning that it's not going to react with anything in your vessel, that's not going to do anything to the equilibrium because it doesn't change the partial pressures of the gases that are involved in the reaction. So if you remember Dalton's law of partial pressures, it says that the pressures of a gas are independent from each other. So you can calculate the individual pressures of the gases, individual gases that are mixed together, and then add them up to a total, because the partial pressure of one gas doesn't affect the partial pressure of another gas. So throwing a noble gas in the mix won't affect the partial pressures of the other gases in your reaction mixture, right? But if you do throw something in there that does react with one or more of the other gases, then that's going to change the amount of that particular substance you have in your reaction mixture, and therefore going to change the concentrations, the volume, or the pressure of that. So then Le Chatelier's principle will be involved in that sort of thing. But as far as an inert gas goes that doesn't react with anything, it's not going to do anything to the equilibrium point or the equilibrium ratio that we're looking at. And then finally, adding a catalyst does nothing to your reaction or the equilibrium point, because the catalyst, as we saw in another video, the catalyst doesn't do anything with regard to the equilibrium of the reaction, but it only brings the reaction to equilibrium faster. So if you throw a catalyst in a reaction vessel, like say, for example, you have hydrogen peroxide. Hydrogen peroxide can decompose into water and oxygen naturally, but it's a longer process. That's why when you have old hydrogen peroxide, it's probably a lot of it's kind of been degraded into oxygen and water, so it's probably not going to be as effective. That process can be sped up with yeast, right? You throw yeast in there with some hydrogen peroxide, the yeast will actually degrade and break up the hydrogen peroxide a lot more quickly, and you'll see bubbles in your reaction pretty quickly, and that's the oxygen being produced. The yeast is only a catalyst. It only speeds up the reaction so that the reaction reaches equilibrium faster, but it doesn't affect the equilibrium point itself. Okay, let's go over a quick example. Okay, let's talk about this example. So here I have N2 plus 3H2 in equilibrium with 2NH3, and it produces this amount of energy. So this is an exothermic reaction. So let's look at a couple of situations. First, add more nitrogen. What happens if I increase the amount of nitrogen gas in my reaction? Well, according to Le Chatelier's principle, it's going to undo that. It's going to relieve that stress. So if I'm adding more of this, then the reaction is going to proceed in such a way to get rid of what I added. So which way is it going to go? It's going to go this way. So it's going to use up some of the N2 I added and produce more of the ammonia, the NH3, to get back to that equilibrium and that ratio that I was talking about. Okay, so it's going to shift to the right. It's going to shift to the right, and it's using up the extra that I put in there by making more products. So it's going to make more products and use up some of the reactants. What happens if I remove hydrogen, right? So I remove the hydrogen instead of adding. In that case, the reaction is going to undo that. So if I remove something, the reaction is going to try to replenish some of that. Which way is it going to go? It's going to go this way to create more hydrogen. So it's going to use up some of this, it's going to break down some of this, and it's going to go and create more of the hydrogen until it reaches that equilibrium ratio that I was talking about. So, and I'll talk more about the math next time in another video, but just the idea of what's going on, if whatever I do, if I change something here, the reaction is going to undo it by doing the opposite, right? So I hope that's clear. So this is part one of my intro to Le Chatelier's principle, and then I'll see you when you watch part two. So please, by all means, if this was helpful, share this video with your friends, like this video, hit that like button, subscribe to my channel, hit that notification bell so you'll be notified by all the videos I put out. Hit that all when you do that. And finally, put a comment down below in the comment section. Let me know what you think. If you've got questions, I'd love to hear them. Thanks for joining me and have a great day.